Hello guys, welcome to the lecture of differential pulse code modulation. Differential pulse code modulation is a signal uh, encoder that uses the baseline of pulse code modulation but adds some functionalities based on the prediction of the samples of the signal. The input can be analog signal or digital signal. Differential pulse code modulation is a technique of analog to digital conversion. This technique samples the analog signal and then quantizes the difference between the sampled value and its predicted value. Then encodes the signal to form a digital value. Before going to discuss differential pulse code modulation, we have to know the demerits of PCM, that is pulse code modulation. The samples of the signals are highly correlated with each other. The signal's value from the present sample to next sample does not differ by a large amount. The adjacent samples of the signal carry the same information with the same difference. When these samples are encoded by the standard PCM system, the resulting encoded signal contains some redundant information bits. The figure illustrates this. The figure shows a continuing time signal xt denoted by a dotted line. The signal is sampled by flat top sampling at intervals Ts, 2Ts, 3Ts and Ts. The sampling frequency is selected to be higher than the Nyquist rate. These samples are encoded by using 3-bit PCM. The samples are quantized to the nearest digital level as shown by the small circles on the above figure. The encoded binary value of each sample is written on the top of the samples. Just observe the above figure as add samples taken at 4Ts, 5Ts and 6Ts are encoded to same value of the 110. This information can be carried only by one sample value, but 3 samples are carrying the same information means redundant. Now let us consider the samples at 9Ts and 10Ts. The difference between these samples only due to the last bit and the first 2 bits are redundant since they do not change. So in order to make the process this redundant information and to have a better output, it is an intelligent decision to take a predicted sampled value, assume from its previous output and summarize them with the quantized values. Such a process is called as differential pulse code modulation technique. If the input is a continuous time analog signal, it needs to be sampled first so that a discrete time signal is the input to the Dpcm encoder. Option 1. Take the values of 2 consecutive samples. If they are analog samples, quantize them, calculate the difference between the first one and then the next. The output is the difference. Option 2. Instead of taking a difference relative to previous input sample, take the difference relative to the output of the local model of the decoder process. In this option, the difference can be quantized, which allows a good way to incorporate a control loss in the encoding. Applying one of these two processes, short-term redundancy, positive correlation of nearby values of the signal is eliminated. Compression ratios on the order of 2 to 4 can be achieved if the differences are subsequently entropy coded. Because the entropy of the difference signal is much smaller than that of the original discrete signals treated as independent samples. If the redundancy is reduced, then the overall bit rate will decrease and the number of bits required to transmit one sample will also reduce. This type of a digital pulse modulation technique is called differential pulse modulation. The differential pulse code modulation Works on the principle of prediction. The value of present sample is predicted from the previous samples. The prediction may not be exact, but it is very close to the actual sample. This is a figure of Dpcm transmitter. The transmitter consists of comparator, quantizer, prediction filter and encoder. The sample signal is denoted by X and TS, and the predicted signal is indicated by X and TS, and comparator finds out the difference between the actual sample X and TS and the predicted value X and TS. This is called signal error and it's denoted by E and TS. Here the predicted value X cap and TS is produced by using a prediction filter, signal processing filter. The quantizer output signal E, Q and TS, and the previous prediction is added and given as input to the prediction filter. The signal is denoted by X, Q and TS. This makes the prediction closer to the actual sampled value. The quantized error signal E, Q and TS is very small and can be encoded by using a small number of bits. Thus, the number of bits per sample is reduced in Dpcm. The quantizer output would be E, Q and TS equals to E and TS plus Q and TS. Here Q and TS is a quantization error. From the block diagram of prediction filter, input X, Q and TS is obtained by sum of X and TS and the quantized output EQ and TS. That is X, Q and TS equals to X cap and TS plus EQ and TS. By substituting the values of EQ and TS from the equation given here, so X, Q and TS equals to X cap and TS plus E and TS plus Q and TS. By combining all this, we get X, Q and TS equals to X and TS plus X and TS. Therefore, the quantized version of the signal X, Q and TS is the sum of original sample value and the quantized error Q and TS. The quantized error can be positive or negative, so the output of prediction filter does not depend on its characteristics. Now we come to receiver of Dpcm. In order to reconstruct the received digital signal, the Dpcm receiver shown in figure consists of a decoder and the prediction filter. In the absenteeism of noise, the encoded receiver input will be same as the encoded transmitter output. As we discussed above, the predictor undertakes a value based on previous outputs. The input given to the decoder is processed and the output is summed up with the output of the predictor to obtain better output. That means here first of all the decoder will reconstruct the quantized form of the original signal. Therefore, the signal at the receiver differs from the actual signal by the quantization error, which is introduced permanently in the reconstructed signal. Now the merits of Dpcm. Bandwidth requirement of Dpcm is less compared to PCM. Quantization error is reduced because of predictor filter. Number of bits used to represent one sample value is also reduced compared to PCM. Now the disadvantage of Dpcm is high bit rate. Practical usage is limited. Need the predictor circuit to be used, which is very complex. Now the application of Dpcm. The Dpcm technique mainly used speech, image and audio signal compression. The Dpcm conducted on signals with a correlation between successive samples lead to good compression ratios. In image, there is a correlation between the neighboring pixels. In video signal, the correlation is between the same pixel in the consecutive frames and inside frames. Mm, this method is suitable for real-time application. To understand the efficiency of this method of medical compression in real-time application of medical imaging such as a telemedicine and online diagnosis. Therefore, it can be efficient for lossless compression and implementation for lossless or near lossless medical image compression. Thank you.